Dr. Karthika is the assistant professor of the Department of Artificial Intelligence and Data Science of Coimbatore Institute of Technology. She has done her graduation BTech in IT from Amrita Vishwa Vidyapeetham and Masters in CSE from PSG College of Technology. She has done her PhD in Information and Communication Engineering at PSG College of Technology. She has worked with Cognigen Technology, India Software Labs, IBM, co-founder of Alarm Technologies, and presently she is serving as the assistant professor. She has published several papers in international journals and conferences, and her research areas include wireless networks using AI and data science in biomedical research. So, with these words, I would like to now move on and over to you, ma'am. And I would like to request you now to start your session. Please, ma'am.
Thank you, ma'am. Good afternoon, all. I'll share my presentation. Hope my presentation is visible to everyone.
Yeah, it's visible, ma'am.
Okay. So I'm like ma'am said, I'm Dr. M. Karthika, and I'm right now an assistant professor in Coimbatore Institute of Technology in Tamil Nadu. I'm working with Department of Artificial Intelligence and Data Science. So I've been in computer science background, but right now I'm working with AI, NDS, and I'm privileged to be here to be part of this faculty development program. So let's move on to the session. So AI and ML, the objective of this session would be to understand what artificial intelligence and machine learning is, to understand the core libraries and tools that is responsible for making this entire section of AI and ML that's happening right now. And we'll be able to see how AI and ML is applied in the field of electrical engineering. And why AI and ML matters today. It's not buzzwords anymore. AI and ML is not buzzwords, some buzzwords that someone is talking about. It's right now actively happening in our lives. It is reshaping our industries by enabling automation, prediction, and data-driven decision making. Its strength lies in its ability to learn from data, uncover patterns, and improve performance over time. So some of the things we have AI-induced devices which we have seen right now which we are currently using are smart devices like Alexa, Siri, and healthcare. We are able to see a lot of applications in radiology, etc. And specifically in electrical engineering, we are able to see smart meters, which is able to predict usage of electricity. Just give me 1 second. Excuse me. So, what is artificial intelligence? So, AI, when we talk about artificial intelligence, it's a science of making machines behave in ways that would be considered intelligent if a human beings were able to do it. So, in simple terms, it's about enabling machines to think, learn, and make decisions just like we do. Actually, AI is a very broad field that includes several specialized areas. For example, machine learning. AI is just not only machine learning, it also includes deep learning, natural language processing, so on. So, machine learning focuses on learning from data. Natural language processing enables machines to understand human languages, and computer vision helps us to interpret images and video. Each of these areas contribute to make machines more capable and useful. And moreover, on top of this, AI is a very generic term. If we closely look at AI, we can look at it in three ways. One is narrow AI, the other is general AI, and the third is super intelligent AI. narrow AI, the first classification of artificial intelligence is narrow AI, where we are right now. So narrow AI will be able to do only a specific task. Say, for example, if I train a machine to
Hello, ma'am.
Sorry, ma'am. There was
Oh,
a small disturbance here.
oh,
So, narrow AI is where we are right now. So, when a machine is trained for only one specific task, where we train a machine to understand to read only the human face, or the machine is able to understand our language, that is a narrow AI. So, general AI would be able to do everything a human being can. So we are able to understand language, we are able to process images, we are able to do prediction, we are able to do some analysis, classification, whatever a human being does. If a machine is able to do everything that we do, it becomes a general AI. So then the next part is our super intelligent AI, where this is a hypothetical situation. We are not even there in general AI right now. So a super intelligent AI would be a hypothetical time where our artificial intelligence will be able to outperform a human being. So this is where our rise of machines, our matrix all comes into play. This is a very hypothetical situation. So these are the classifications of artificial intelligence. So when we look at AI, there are a lot of terms associated when we talk about artificial intelligence. We say something as artificial intelligence. Machine learning is closely associated with artificial intelligence. Then we move on to something called deep learning. Then we have something called data science. So what do these terms represent? The biggest circle, the artificial intelligence, the largest circle here is a broad field. Is a very broad field that covers everything related to machines, making machines very intelligent. When we are able to impart our intelligence to any machine, it becomes artificial intelligence. So when we say machine learning, we talk about a specific subset of artificial intelligence where a machine uses data and it's able to use the data to make itself intelligent. It'll use the data, it'll learn from the data, and after learning from the data, it'll be able to predict something for us. It'll be able to classify something for us. It'll be able to do something for us. So this part, which uses data and to become intelligent, comes under machine learning. And this is a subset of artificial intelligence. So next is our deep learning. So deep learning is a subset under machine learning where we use very complex neural networks. A neural network is built closely in association, works like how the biological neurons inside our brain works. So our brain is actually the model behind deep learning. So deep learning is a subset of machine learning where there are large layers of neural networks and it is able to do very complex tasks like image processing or understanding human language. These tasks will not be able to be performed under just machine learning. So we need a very complex network of neurons to do this. So this subset of algorithms that does this comes under deep learning, but this in turn uses data. So this is generally also a machine learning also. But since machine learning aims to make a machine intelligent, it falls under artificial intelligence. So all these terms have these meanings. So where does data science come here? So data science, if I have to represent data science as a Venn diagram in relation to this, I'll be drawing another circle which will cover artificial intelligence, machine learning, and deep learning. So data science will make use of the data and it will use machine learning algorithms as well as deep learning algorithms to do data processing tasks. So these are the terms associated with AI. So now let's talk about machine learning. We'll move on to, since now we have understood what artificial intelligence is, we'll be moving on to something called as the next thing, which is called as machine learning. So machine learning is a branch of artificial intelligence, like I said, where the computer system learns from data rather than being explicitly programmed. Like for example, before artificial intelligence, whenever we wanted the help of a computer, we would be explicitly programming it. Say, for example, let's take an example of a traffic signal. So I'll be programming the controller inside the microcontroller inside a traffic signal, saying that let 30-second pass. So after 30-second, you switch on to green light. After 30-second, switch on to yellow light. After 30-second, you move on to green light. So this is how we program it. So the system will not bypass or will not disobey my program. So whatever I've asked the system to do, it will just do exactly that, not lesser than that or not greater than that. Whereas when I talk about something called machine learning, I give the data to the machine will learn the data, and without me explicitly telling what the machine is supposed to do, it will start doing the work. Let's say, for example, there are a lot of things a machine learning algorithm can do. For example, a machine learning algorithm, after it learns, can classify something, whether this is good, this is bad, whether the student will pass or a student will fail, or something it can predict. That comes under classification tasks. The next task that it can do is called as a regression task, where the output is where the machine will emit a continuous value. For, let's say, for example, I have the real estate housing prices happening in Kolkata. So I'll give the area name, I'll give the number of rooms present inside a house, I'll also give the square feet of the house, I'll feed the machine with, I'll also give the price, I'll feed the machine with this data. After learning a lot of such varieties of data, after a certain point, when I give a new area, when I give let's say, for example, when I give an area and when I give a hypothetical number of bedrooms, it will be able to predict a price for me. That comes under regression tasks. So clustering is actually used when I don't have any labels. Say, for example, it groups similar data. In India, let's we have so many people, more than 100 crore people right now living. Not all of us have insurance. So if we take the entire population and feed it to a machine learning model and we do not say anything about it, the machine learning model will automatically categorize these will be the data points. We people will be the data points. It will be grouping us. So these sort of people will be buying insurance, medical insurance. These sort of people will not be able to will not be buying medical insurance. So clustering algorithms, clustering part of machine learning will automatically categorize the data points into groups. So whenever a new person comes in, the model will accurately tell me that, okay, this person is close to this cluster, so there's a high chance of this person buying insurance. This is how clustering usually works. So recommendation systems will suggest items to users. Think of how YouTube recommends video or Amazon suggests products. These systems learn from our past behavior and preference, and it will tell what it will give us suggestions for our future. This is how recommendation tasks works. Another category of machine learning is anomaly detection. This involves identifying rare or unusual patterns. It's widely used in fraud detection, network security, predictive maintenance. All these type of tasks comes under anomaly detection. Natural language processing. Natural language comes when the machine is able to understand the human being's language. The way we talk, the way we emote, the way we present, even sign language is actually a natural language. The machine will be able to understand, even if I'm not able to talk. If I use a sign language, the machine should be able to understand what I'm talking to it and be able to give a certain type of output based on that. So that will come under a machine learning task. So computer vision, this we're extensively using, where we use facial recognition in our iPhones everywhere. These comes under computer vision tasks, where machines are able to interpret the images. It's able to understand the image, or it's able to understand a video. One case is like in a crowded place where there was COVID, the traffic cameras can automatically, it's a live feed, people moving, it will be able to automatically determine whether someone is wearing a mask, whether people are following the correct social distance. All these tasks, the machine will be able to tell whether social protocols are being followed. All these tasks come under computer vision. So all these are subcategories of machine learning. The other important, which is very essential for electrical engineering, is time series analysis, where Time series comes under where my data is a function of time. Say, let's say for stock, my Apple stocks, the price of my Apple stock moves for every second, and my the data from my sensors move every second. My EEG data, my ECG data, all these data which moves in accordance with time, and my computer is able to, when my machine is able to make do certain type of task based on such type of data, is called as time series analysis. So all these are categories, or all these are the ways in which machine learning can actually help us. It can do all these tasks. This is a very narrow classification of machine learning algorithms. And when we there's another way of looking at machine learning. We can classify it into three types. One is the supervised learning, the other is unsupervised learning, the third is a reinforcement learning. So when I talk about a certain algorithm and call it supervised, I'll be telling that, let's say, for example, I am able to, we'll take the case of the grade point acquired by a student and the number of hours he has put in before for the examination. So what I'll give to the machine is a collection of data of 100 students. I'll tell that these 100 students, for each student has studied these for these many hours, and this student has acquired this CGPA. So I have labeled, I know what I'm actually feeding, and I'll also know what I want as an output from the machine. And after this, using this data, if I use it to train the machine and then give another data, say this student has studied this many hours, can you predict the CGPA of this student? Such type of tasks comes under supervised. So supervised learning is a type of machine learning where the machine knows and the user knows, the programmer knows what is given as input and what is expected out of it as an output. This is supervised learning. Unsupervised learning is when I'll not give any input to my machine. I'll just randomly throw in data. The machine has to, by itself, has to understand the hidden patterns inside the data. So I'll not tell this is your input, this is your output. No, I'll not say all those things. That my, for example, the example which I told, where people are the 140 crore people in India who will be buying medical insurance will come under this, because I'll just give the data to the machine. The machine by itself will start to cluster. It will find the pattern among the people who are buying insurance and the people who are not buying insurance. So the machine will automatically do by itself without me supervising the machine. So those sort of examples comes under unsupervised learning. So reinforcement learning is when my machine, an agent learns by interacting with an environment. It receives rewards and penalties based on its actions it takes and learns to maximize its efforts. For example, robotics comes under this. My self-driving cars comes under this. We have a robotic vacuum cleaner. You know, it goes and it receives penalties, and when it hits a wall, it receives a penalty. When it's moving in the correct direction, it receives an award. So this is how the machine learns from the environment. Such type of algorithms comes under reinforcement learning. So these are the types of machine learning algorithms. So I'm not going into every machine learning algorithm, since I've seen that the upcoming sessions cover a lot of such algorithms. I'm just covering what are the types of algorithms and what machine learning generally does, and what are the tasks that I'm supposed to do for building a machine learning model. So, so this part, AI and ML in electrical engineering, since we are running very short of time, so I'll be covering this after after seeing at how I'm supposed to build a machine learning model. How there is a set of activities I'm supposed to do. Using those activities, I'll be able to fit a model and make the model work for me. So after covering that, probably we'll be coming back and looking at the applications of machine learning in electrical engineering. So right now we saw the types of algorithms, the types of tasks machine learning can actually help us with. So what are the tools that are actually available for us to make this possible? The most famous one is the Python. So Python, with its extensive library support from throughout the community, throughout the world, we have a very extensive support for Python, and it's the most important, most popular machine learning language. Actually, it has a extensive library support. We can't imagine the type of support we get when we use Python. So there is one other a tool called R. R programming is mainly a statistical tool, mainly used for statistical data analysis or visualizing statistical plots. We use R. So Java comes in because certain times when we need to for the machine learning to work with cellular phones, we will not be able to use Python. Say for example, I download a PDF and I need my system to classify whether my machine learning model, which is present inside my phone, to classify the PDF whether I've downloaded is a spam or is a malicious piece of PDF, or is it a trustworthy PDF. So such type of tasks has to run inside my cell phone, and I need Java for that because it runs in Android and I need Java. So we have an extensive support in for machine learning in Java also. And for academic purposes or electrical and controls engineering, we also have MATLAB, which can be used for machine learning. So, what are the Python libraries? So, we will be taking a close look at the Python libraries which are available for us. The most famous and the where we start using Python is with NumPy. So, NumPy is a library which helps us to easily work with arrays, higher dimensional data. So, it also does complicated mathematical operations. So, this NumPy helps us. And Pandas is also another library which helps when we have tabular data, which rows and columns. Most of the real world data comes as tabular data, and this Pandas has extensive support, gives extensive support to work with tabular data. So there's something called as Dask when the data set is very, very high. When I'm supposed to do parallel compute, a lot of parallel computations are involved, I can always make use of Dask. And there's a specific, a lot of real-time data is available in Excel. So there's a specific library called OpenPyXL or XLRD, which is specifically made to handle Excel file. And other libraries are Matplot. This is for data handling. NumPy Pandas is for when I have a raw data, how I'm supposed to work with the data. All these libraries help me with that. Other libraries which help me make sense of the data by visualizing the data, how it looks, what are the outliers, what is a mean, what is a median, where are the null values. If I have to look at all these values, I'll not be able to look at only the raw data. I need a visual form. Visual form helps me to understand my data set better, whether I can properly make use of this data set or not. So to do this, Python gives me Matplotlib and Seaborn, which gives statistical plots, and Plotly and TensorBoard. TensorBoard is specifically used for visualizing neural networks. So this neural networks will come under deep learning, where I'll have multiple layers of neurons, hidden layers of neurons, which helps me to accomplish very complex tasks. This TensorBoard will help me visualize how those neural networks work. So the other libraries are machine learning. For now, we have saw for data visualization. As for data handling, when we want to take and build a model, the following libraries would help. Scikit-learn, which is used for regression task. Like I said, regression is used for predicting something. So classification, let's say for whether I'm classifying something as spam or not spam. Clustering is grouping certain type of data points together. For all this, I can use Scikit. Then I have XGBoost, LightGBM, and CatBoost for gradient boosting. This all comes under my machine learning models. And when I have a data set which is imbalanced, which is not properly it covers only a certain, when the data set itself has a bias, meaning only the data is covered only for a few samples very well. In those cases, I can use a library called ImbalanceLearn. This will help me in fitting a model even when the data set is quite imbalanced. Then for feature selection, I'll tell you what is feature selection. Let's take an example for the house price prediction, like we saw. So let's say a house, when I have the data, the features which are available are the number of the area which is located, the number of bedrooms it has, the square feet it has, and the number of trees surrounding it. Let's say number of parks located close to the house. Among all these 5 features, only 2 or 3 is very useful for me to predict the price. For example, let's say only the square feet and the number of bedrooms, as well as the area in which is located, will determine the house price, not the number of trees present in the house or the park is close by or not. These features do not help me in correctly predicting the value of the house. So feature selection is one area, one part of machine learning. While selecting the model, I'll have to do something called as feature selection, which extracts only the important features. So for doing this, my ML extend will help me. This library in Python will help me in that. So this is for till now what we saw was for machine learning. For deep learning, I have something called TensorFlow. This is the most commonly used library for deep learning. TensorFlow, it's very famous. And I have Keras. This is also for building neural networks. PyTorch, which helps me build dynamic graphs, and Fast AI. This is when I do not have a lot of time for training the model, and I have very short time to train the model. I'll make use of this Fast AI. So till now, what we saw, what are the libraries which is available for which will help me build a machine learning and a deep learning model. Now we'll have a series of steps which I'll have to take in a series for me to achieve a certain goal. So, say for example, I have a task which I think machine learning can help me solve the problem. So, what are the steps I need to do in order? The order of these steps is very, very important, it's highly crucial. So, what are the steps I'm supposed to do to make this model work? So, the first step is my problem formulation step. So, problem definition. Okay, is the model actually apt for is this task actually apt to solve by machine learning? Because a simple model like controlling the traffic lights do not need something very sophisticated as a machine learning model. When I say measuring height and weight of a person and digitizing it, I do not need machine learning. So when I have a problem, the first and foremost step is to determine whether this problem is actually solvable through machine learning and whether machine learning is actually needed for this problem. So any problem which needs human like intelligence only needs machine learning. So we need to first understand the objective of the problem, and then we'll have to start doing the other steps. The next step is the data collection part. So data collection part, we'll have the data mainly comes from my real-time data actually. So because machine learning is not a very theoretical practice. It actually works in real time. Highly, it works in real time. So every data I'll be working will be coming from real world. So the sources of such data would be like sensor data, namely the voltage, current, temperature, and historical logs from electrical equipment. Sometimes the data would be coming from EEG from electroencephalograms, or the ECG data, or I'll be getting billions of records from flight sensors, the sensors from the wings of a flight. Every part, every sensor, every data entry is data. So the sources really depend on the problem objective. So looking at the problem objective, I should be able to pick out the source points of my data, which data should be really accurate for me to make this model work. So the type of data is structured, meaning tabular. Sometimes it will be very unstructured data, like randomly I get electrical signals from the brain. It's very unstructured. And the challenges would be the main challenge. See, a machine learning model is like a mirror. So when I feed gold, it'll show gold, it'll emit gold. When I feed garbage to the machine learning model, it'll throw garbage back at me. So the data is the real gold. The quality of my data will help me determine the outcome of my machine learning model. However good am I a programmer, however good I'm able to fit the model, how much ever I have done perfect optimization, perfect feature selection, nothing of that matters if my data is not very good. So the raw material is the most important step in while creating a machine learning model. So the main challenges includes, most of the time the real world data comes with a lot of noise. When we say noise comes under irrelevant data or missing values, or the data is corrupted. All these things comes under noise. And the second issue is data privacy and security. One of the a very sensitive area where machine learning and deep learning can really help people is in healthcare. But the healthcare industry is the toughest place to get the data set from. So when we want to make accurate predictions, we need the most perfect data. But I've known people who have struggled for months together to even get a few basic data set from hospitals. So it's very tough. And the real-time data, collecting real-time data is also very tough. We need to clearly know where to collect the data and how to correctly store and collect the data and store it properly. So, like I said, in projects like quality matters more than quantity. A well structured, clean data set can lead to better models. In projects like load forecasting or fault detection, the accuracy of data from smart metals or transformers is very crucial. So, we should always consider where and how our data is generated. Is it real time? Is it stored? Is it stored locally or is it stored in the cloud? All these decisions impact the entire pipeline. So after defining the problem, after collecting the data from the real time, then we move on to something called as data pre-processing. So data pre-processing is where most of the effort in any ML project goes. Poor quality of data leads to very poor results, meaning I might have gotten real gold ore, but extracting the gold from the ore is very important. So not so the diamond is present inside a carbon, but a carbon cannot become a diamond. So the polishing of the removing the carbon outside and removing the diamond is the hardest part in extracting the diamond, not the mining process. So after getting hold of the data, however good source it is, the important step and the time consuming and the hardest step is our data pre-processing step, not even the model building part. So what I'm supposed to do when I say I have to pre-process the data, I say that I have to handle the missing values. Like I said, the data is very noisy. A lot of the times, important parts of the data would be filling. So I have to make a decision whether I have to remove the data or should I calculate the median and fill it, or should I calculate the mean and fill it, or should I completely neglect such type of data. I have to handle the missing values. Then I'll have to remove duplicates. That's called data cleaning. I'll have to, sometimes there might be duplicate entries. This is very important because it'll entirely shift the model's focus. When I do not do such process, it will shift the model's focus, and the output of my machine learning model without pre-processed data and with pre-processed data is hugely different. So I'm not supposed to skip any of these steps. So I'm supposed to remove the duplicates, and I'm supposed to, if there are any inconsistencies in the data, I'm supposed to fix it. And this normalization part is very interesting. Let's say, for example, when we are dealing with voltages, I have something close to 10,000 volts, and somewhere the temperature, one of the features is voltage, and the other feature, let's say, it's temperature. The temperature closely will go to 100 degrees Celsius, but my voltage can go to 10,000, 20,000 volts. My model will, simply by looking at the number, my model will automatically think that, okay, voltage has a very high number, so this feature is very important. My model will incorrectly make an assumption. We do not know whether the temperature is really important as well. So just because my temperature is a smaller number, my model shouldn't understand that. My model shouldn't think that, okay, the temperature is not important, probably only voltage is important. So when there is huge difference in the numerical numbers, I'm supposed to scale it down so that the model doesn't show any bias to any specific feature. I'm supposed to do that. And then I have to do encoding. Certain types of models do not will not work with all the categories of data. So I'm supposed to encode the data. Say, for example, male and female, my model will not able to understand. It needs a numerical value. Everything I'll be calculating using matrices. My matrices will not be working with categorical data. It needs numbers to crunch. So I have to encode the data. And after that comes my feature selection. Feature selection is, like I said, whichever features is very important for me to do the machine learning task, I'm supposed to do it. Only then my model will be able to do it, come to a correct conclusion, as well as come to a conclusion very quickly. Only if I do a feature selection. So this part is also very important. So the next step is model building. So like I said, suppose I have a problem of predicting whether electrical smart let's say I have a problem of predicting the wind area. There is a wind turbine running, and I'm supposed to predict what will be the wind speed tomorrow. For here, I should not be able to do a regression task. I should not be able to do a I shouldn't do a classifying whether wind will be there or not. I should be able to predict what is the actual wind speed that will be happening. So here I'm not supposed to take a classification machine learning model and start building it. I need to know whether I need to go for a regression model, classification model, or clustering model. Here I need a continuous value. So I need to build a regression model. So you, based on the problem objective, I need to choose the correct model and start using the data to build the machine learning model. So unless and otherwise I do not use correct model, my output will not be right. It's like bringing a very big bulldozer to remove a small weed of plant. It's not necessary. Looking at the problem, I should know that which screwdriver I have to bring. I shouldn't directly go and bring some other tool to do something. So that is very important. Then the next step after choosing the right model is dividing the data. Now I've got the data, I've got amazing data, I've done all the beautiful work to clean the data, I've pre-processed it, I've removed all the missing values. When there are noises, I have cancelled everything, and the data is beautiful, and I've also chosen the perfect machine learning model. What is my next step? I'm supposed to split my data into training and testing. So training data is what my machine learning model will use to learn. So it'll continuously imagine this like that. So imagine I have a kid, and the kid, I need to teach the small child to identify the image of a cat. So let's say I have 10 images of a cat, and to the small kid, I'll be taking 7 pictures of the cat, and I'll be showing to the small child saying that this is a cat. The second time I'll say that this is a cat, this is a cat. So 7 images of cat I'll show to the kid, and remaining three out of the 10 images, the 3 images I'll be showing it to the kid to ask to check the kid, to test the kid. I'll show it to the kid, and I'll ask him what is it. It should correctly say as cat. So if my data set totally has 10 images closely, it's usually 80 to 80-20 split. 8 images I'll be using it to train the kid, and 2 images I'll be using to test whether the kid has actually understood. This is actually machine learning, how kids learn. Actually, machine learning was AI is built basically on how children learn. That's how artificial intelligence has actually come. So the children, when they are born, when they are born, they do not have any knowledge. But repeatedly, when they are seeing things or when they are hearing the language spoken, neurons gets formed inside them, and they're able to identify the patterns. They're able to identify, okay, this noise means this thing. Amma, the sound Amma means I'm calling my mother. That's actually a data meaning something. That's how a machine also learns. So I decided I took my data set, I split it into 80-20. So what I'll do based on my model, I'll be choosing the features, and I'll be selecting the algorithm, and I'll be feeding my data inside my model. My model will perform very badly. It will not give me accurate results. I'll use the result, and I'll again use the result to train my model back. So it goes back and forth. So it learns after a certain point. The main characteristics of a machine learning model is over and over in a certain period of time, my machine learning algorithm would start behaving better. That's how ML model works. So initially it will spit out some garbage result. I'll use that garbage result, and I'll tell it to the model that, see, this is not good. You're predicting it wrong. The value we have used is not right. So rearrange yourself and make sure you're giving a good result. So repeatedly I'll be taking the output and feeding it back inside the model, and the model repeatedly will learn that, okay, what I have done is wrong. What I've done is wrong. Probably I should change this and see. So finally, over time, my model will be able to tell that if you give any input, it will be able to give you a correct output. After 8 pictures, then for the 9th picture, the kid will be already ready to tell it is a cat. That's how a machine learning model works. So these are the common algorithms which we work. Linear regression is for regression. Decision tree is for classifying something. Random forest is also something like that. K nearest neighbors is for clustering. Neural networks comes under deep forest. All these algorithms will be actually taken in the later sessions of the faculty development program. But right now, we'll be looking only at the pipeline. So we have built the model, and after building the model we just can't simply say that okay, a model is built, we can start using. We need to evaluate the model. We need a scientific way of telling whether the model's behavior is correct or not. We cannot just simply trust the model. We need to evaluate it. For evaluating, we use a lot of metrics like accuracy, how accurate the model is, how precise recall. These are some of the things which we use to evaluate the model: precision, recall, F1 score, confusion matrix, telling how many positives it's actually correct, how many false positives it gave, meaning the value was supposed to be a different, but the machine learning model gave it to be a positive one. So confusion matrix, all these things we calculate. And root mean square error is a common evaluation metric when I'm supposed to predict a continuous value, what the value is supposed to be, but what my model is actually building. The difference, the error difference between the two gives my root mean square error. So the main aim of my model is to bring down all these error factors and perform well. So this is how I evaluate my model. And after this comes my model is built. I've collected everything. I've chosen a Paka model. I've trained it well. My model is also based on the evaluation metrics. My model is also performing well. So after this, what am I supposed to do? This model has to be present has to be implemented in the real world. For that, I can actually use it. Let's say I deploy spam filtering or detecting something is malware or not in my phone. So I'm able to embed this model inside a device, or I'm able to embed this model in the wind turbine. Let's say predicting the the force of wind for tomorrow, I should be able to build a model and fit it inside my turbine, inside a microcontroller inside my turbine. So the platforms which helps me with these deployments are AWS, Azure, Google Cloud I can use. And we have to consider the following things. Just because I'm able to, AWS sounds fancy, I cannot build and deploy a model inside AWS, because it will again create a lot of problems like latency, and the time taken to communicate back and forth between my model, when my machine, the actual machine, as well as the AWS, it can be high. Sometimes the results need to be very, very, very time critical. So all these things I have to take into consideration. So depending on how critical the time is, or how am I restricted with related to budget, or how am I are there any constraints to me, I'll determine where the model should be actually deployed. Is the model sophisticated in it, or do I have enough budget to deploy it somewhere, and do I have the sophistication of time to get it from there, or I have to make the model very tiny and be able to fit it inside a small sensor device also. We should be able to do that. Only then the success of a machine learning model actually comes true. Then after this, this is one of the case study where General Electric used. So before this, I'll be moving on to some of the cases where AI/ML is used in electrical engineering. So, in power systems, to predict the future electricity demand, a machine learning can be used. So, when there are any faults in my transmission lines or transformers, to predict that, to detect that or predict that, I can use it. And smart grid, if this is one of the things Sir said, where where the distribution, like how the energy has to be distributed, it can be optimized using smart grid. Or when there are any anomalies, suddenly there is an energy theft in electrical energy, those things can be detected using machine learning algorithms. These things can be used in power systems. And next, in renewable energy systems, like I said, for during the solar and wind power generation, I can be able to predict previously how much of energy will I be able to generate based on the data that is available, weather data that is available to me. Using the weather data, I should be able to predict how much of energy can be actually generated. And battery management systems is also another one where machine learning can be extensively used. And control systems and automation, where the controllers can be self-tuned, can be made to self-tune. And process automation is where one of the things where machine learning can be extensively used. And one another problem is when I'm able to accurately predict whether a machine can actually stop working or can go into a failure before the actual failure happens. That can be actually predicted using machine learning. Sometimes computer vision can also help, looking at the images of bearings or looking at images of certain parts of a machine, a very big machinery. before the failure actually happens, the system can actually warn the stakeholders that the machine is going to go into a failure. All these things can be done. And signal processing and communication, it can actually classify the type of signals or whether it's a noise or a signal using machine learning techniques, or it can use deep learning to improve the accuracy of signal transmission over a very noisy channel. And other areas where it can be used is, like I said, it can be used to diagnose faults, or it can use predict the failure of machines, or it can be able to monitor health of the machines. All these can be done. And this, like I said, industry 4.0 is right now taking over everything. Our engineering disciplines are all becoming interdisciplinary. So AI driven robotics can be done, automation can be done, and anomalies can be detected. Quality control can be used for computer vision instead of manual intervention for computer vision tasks. Quality control can be automatically done using computer vision. The systems can be automatically predict whether the manufactured materials is okay or not. So all these things can be actually done. So these are some of the research areas in electrical engineering discipline. And the case study which I was talking is how General Electric has actually used machine learning to significantly reduce their energy and energy actually. So what they have done is they have implanted wind turbines in very harsh environments. So manually going and inspecting them and maintaining them is very costly, and unexpectedly failures happens, it'll lead to a lot of energy loss, actually revenue loss basically. So what they did was they used a machine learning model to predict the machines going into failure, or predict maintenance, whether maintenance is needed for the wind farms. So they collected data from the turbine blades, the gearbox is generated, and they used the historical, already they would have had data from failures, so they would use that data, and they'll also use weather data. All these data they have used, and they have taken, this is a time series problem, because continuously we get data from the signals and we are supposed to predict it. So they used a classification algorithm saying that whether this will go into failure or not. So that comes under classification, and they have actually used this model to improve to reduce maintenance costs as well as improve energy efficiency in while wind farming. So this is one of the use case of where General Electric has successfully used machine learning in electrical engineering. So the summary is like, it's not, AI and ML is not a buzzword anymore. We are doing, without even us knowing, we are doing it every minute of every day. So machine learning basically works with data. So data is everything for a machine learning. It just looks at the data, learns from it, and starts behaving like a human being. That's how machine learning actually works. And the most important libraries are, like I said, are NumPy, Pandas, TensorFlow. All these libraries are extensively used. And we also looked at the pipeline where I'm supposed to identify the problem, collect the data, pre-process the data, clean the data, pre-process the data, build the model, evaluate the model, and finally go and deploy the model wherever I need. And we also looked at the real world applications. That's it.